Welcome back and thank you for joining me in this lesson. In this video, we'll begin learning how to solve polynomial inequalities starting with first degree or linear inequalities. Recall from the first part of this lesson that solving polynomial inequalities is very similar to solving polynomial equations. To make that comparison clearer, I've displayed the algorithms for solving both linear equations and linear inequalities side by side. So let's compare the steps. Step number 1, we expand and simplify both sides. So this step is the same for both equations and inequalities. Step number 2, move all variables to one side. Again, there is no difference between solving equations and inequalities. Step number 3, we have to move all constant terms to the other side. Once again, the process is identical. Step number 4, combine like terms. This step is also the same for both. Now let's look at step 5. At first glance, it appears that both steps are the same. So for linear equations, we isolate the variable. For linear inequalities, we also isolate the variable. However, this is the one step where we need to be especially careful, and that's why I wrote the note in here. There are two important rules to remember. Number 1, if the coefficient of the variable is positive, then we solve the inequality exactly as you would solve an equation. So there are no changes to it. But if the coefficient happens to be negative, you must reverse the direction of the inequality symbol when you multiply or divide both sides by that negative number. Let's see why this rule is necessary with a simple numerical example. Consider numbers 3 and 5. We know that if we were to compare these two numbers, we would say that number 3 is less than 5. If you place them on the number line, let's say this is 0. If number 3 is here, number 5 will be further to the right. Now, switch their sides. And the reason why we want to observe this is because when we solve linear inequalities, we want to take terms, constant terms to one side and variables to the other side. So switching terms from one side to the other is very important to analyze. Now, if you switch the sides of the terms, then we have to switch their signs as well. So 5 becomes negative 5 and 3 becomes negative 3. So when you read this statement again, negative 5 less than negative 3, we're going to say that it still holds true. And that's because if you place these two numbers on the number line, then you know that if negative 3 is here, negative 5 will be further to the left side of it. So negative 5 is less than negative 3. Now, when solving inequalities or equations, often we have to divide by the coefficient of x to isolate the variable at the end when we solve it. So now to observe what happens to inequality now, we're going to divide by negative 1 because this is what we had a problem with, a negative coefficient. So if you divided both sides of this inequality by negative 1, and by the way, the same thing applies to multiplying by negative 1, then negative 5 divided by negative 1 will be 5, and negative 3 divided by negative 1 will be 3. So we're looking at the same statement in here, which is less than. So I want you to compare. Is 5 still less than 3? Is the statement true? Then you can easily say that the statement is not true anymore because if you place these two numbers on the number line, suppose this is 0, here is 3, the number 5 will be further to the right, which makes number 5 actually greater than 3. So notice that the direction of the inequality now has changed. And the reason why it changed is because we divided both sides by negative 1. That's the only difference or the only thing we did different to go from this step to the other. So in conclusion, we're going to say that when solving inequalities, transferring terms from one side to the other will not change the direction of inequality. But whenever we multiply or divide both sides of an inequality by a negative number, the direction of the inequality must be reversed in order to keep the statement true. So now let's take a look at an example. We have to solve the linear inequalities, graph the solutions on the number line. We have the number lines provided for us and express the answer in both set and interval notations. So our first example is 35 minus 2x greater than or equal to 20. So we're going to start off by grouping the variable terms on one side and the constants in the other. So as you can see, there is no simplifications that need to be made in each side of the equation. It's a simpler inequality, that's why. So we're going to take 35 to the other side, and that will change its sign. So simplify each side because we want to have only one term on each side of the linear inequalities, just like in linear equations. And 20 minus 35 will be negative 15. Now we'll divide by negative 2, both sides of the inequality so that we can isolate x. And notice that we are dividing by a negative number, which means that the direction of the inequality now will switch to become less than or equal to, and negative 15 over negative 2 would be equal to 15 over 2, or simply 7.5. And I would write this in decimal form this time because dividing 15 by 2 does not force me to round the answer. 7.5 is exactly the same. And also when I draw the solutions on the number line, I need to know the decimal value. It's harder to locate the fractions in there. So how do we draw this on the number line? Let's take a look. So we have to first spot where number 7.5 is. And notice that 7.5 is part of the solution. So when you plot 7.5 on the number line, here is 7 and here is 0.5. We have to draw a filled circle. Now, the values of x are less than 7.5, and some people like to actually just draw an arrow in here to indicate that the rest of the numbers will be in this direction. But I find that when we are using paper and pencil in class, it's kind of hard to see it, so we have to be extra, firm with the paper and everything. So I like it when we do it this way better so that we can make it more clear that this is a set of numbers we are talking about. You want to draw an arrow because the numbers will continue towards negative infinity. So when you write the answer in set notation, then we're going to say that x can be any real number or belongs to the set of real numbers such that, and that is this slash line in here, and the only number that we have in here, the only boundary we have is 7.5. So we are comparing x by 7.5 only. And we have the inequality right here, the solution. That will be part of our solution in the set notation. Now, in interval notation, on the other hand, we're going to say x belongs to. Now, remember, intervals are read from left to right. And on the left side of this set of numbers, we have negative infinity because the numbers will continue to negative infinity. The right side, we have 7.5, and 7.5 is indeed included. Remember, around negative infinity, we always use round brackets, and we separate these two items inside the brackets by a comma. So we're going to write round brackets, negative infinity, comma, 7.5, and please use square brackets around 7.5 to indicate that it is part of our solution. So the next example is for you to try on your own, so you can stop the video and give it a try, and I will continue explaining it in here. So just like we did in the previous example, we're going to keep x to the left and numbers to the right. So 12 will come to the other side and switch the sign to opposite. So now we have negative 5x less than, this will make it 22. So we have to divide both sides now by a negative 5 to isolate x from its coefficient. And notice that division is by a negative number here, which means that it will change the direction of the inequality, and that's because of the negative again. And 22 divided by 5, since we want to actually draw this on the number line, is 4.4. So we are going to find where 4.4 is on the number line. So I see that 4.5 is right here. Sorry, that is a mistake. So I almost missed it. So that would be negative 4.4. So negative 4.4 would be somewhere in here. So this is negative 4, negative 4.5. So a little bit to the right of negative 4.5, so somewhere in here. And we're going to remind ourselves that this number shouldn't be part of the solution because only greater than negative 4.4 are parts of it. So the circle will be empty, and we'll draw our little line in here to indicate the rest of the numbers are greater, so to the right of negative 4.4. And this is how you would graph this. So we're going to start at negative 4.4 and end to infinity. So in set notation, we're going to say that x can be any real number such that x is greater than negative 4.4. Close the braces in here. That's the name for these squiggly brackets, braces. And write the answer in interval notation. So in interval notation, again, we're going to write the solution from left to right. The leftest value we have is negative 4.4, so we'll write that down. And the rightest value we have is infinity, so we'll write infinity, separate by a comma. Negative 4.4 is not part of the solution. Infinity always has round brackets, and that would be the answer in interval notation. So now let's continue with another example. And in this example, as you can see, we have a little bit of a bigger equation. So we have to first expand and simplify each side of the inequality. So we have 3 times 2x, 6x. And then we have 3 times negative 5, negative 15. Now, here we have a minus. You can imagine an imaginary negative 1 that is multiplying every term. Or you can just remember that when you have a minus before the brackets, remove the brackets and switch the signs of the terms inside. So that would be minus x minus negative 2, which is plus 2. Less than or equal to, so here we have 2x. Here we have 6, and then minus 5. Now we'll simplify each side, which means we're going to group together the x terms and the constants. So 6x minus x is 5x. Negative 15 plus 2 is negative 13, less than or equal to. And then we have 2x plus 1. Now we'll group x variables on the one side of the inequality and the constants in the other side. So we have 5x minus 2x equal to 3x, less than or equal to 14. So we're going to say that to isolate x from 3, we divide both sides by it. And as you can see in here, in this case, we do not divide by a negative. It's a positive number, which means that the direction of inequality will stay the same. And we're going to say x less than or equal to 14 over 3. So this is going to be a never-ending decimal number, but I am going to make note of how big a number that is, 4.6, and the reason why is because we want to graph this answer. Now, when you graph this answer, then you're going to have to find where 4.6 is, so a little bit more than 4.5, as you can see, and all the numbers will be to the left of it. So we're going to go in this direction. So this is where all the solutions will be. So this is negative infinity, and this one here is negative, 14.3, I meant. So in set notation, we're going to say x any real number such that x is less than or equal to 14 over 3. When you write the solution in set notation, we must write the answer in exact form in here. So the decimal value just helps us locate where the point will be or where the boundaries are. Now in interval notation, same idea. We have to use exact values. We're starting from negative infinity and we're finishing at 14 over 3, and 14 over 3 is included. So we're going to write negative infinity, comma, and 14 over 3, and then close the brackets. Make them square, please. Now you have another example here. You can try this on your own. So let's do this together though. So you have 3 over 2x and then 3 over 2 times 4. So let's write this down. 3 over 2x plus 3 over 2 times 4 would be equal to 6. And now we have negative 2x and then plus 6 greater than or equal to 1/2 x and then plus 3. So we'll take all the terms to one side of the equation. I see some are in fraction form and some are not. And I am hoping that by combining them, we will eliminate the fractions without having to do the lowest common denominator. So that's my strategy at this point. So 3 over 2x minus 1 over 2x minus 2x greater than or equal to, we have 6 plus 6, 12. And on the right side, we have a 3, so minus 12 in here. So these two 6's will make the 12. Well, surprise, surprise. Let's see what we get in here. So 3 over 2x minus 1/2 x will be 1x. You see that? So 3 minus 1 divided by 2 is 2 over 2x. So we got rid of the denominator. So positive 1x minus 2x will be negative x, greater than or equal to 3 minus 12, which is negative 9. Now, it looks like x is isolated, but not exactly. It does have a negative sign, which means the coefficient is negative 1, and we want the coefficient to be exactly positive 1. It's a very easy number to miss, or coefficient to miss, and that's why I brought this example. And it is the easiest problems that where we make most mistakes because our guards are off, and we continue solving following our first impressions in a way. So remember that we are dividing by a negative, which will change the direction of the inequality to less than or equal to, and negative 9 divided by negative 1 will be positive 9. Now, let's draw this on the number line. This is a very nice solution. And here is number 9. And the rest of the values will be less than this. So all the x values work for that inequality will be anywhere from negative infinity to 9. So in set notation, we're going to say x is any real number such that, and we're going to say that x is less than or equal to 9. You simply write whatever solution you get in here for the answer in set notation. In interval notation, we're going to say that x belongs to the interval starting from negative infinity, comma 9. Don't forget square brackets around this. Now, next we're looking at double inequalities. Now, what are double inequalities? Double inequalities are basically all linear expressions that are connected to each other in an inequality that contains two inequality symbols. Now, what does that mean, really? Well, what it means is that double inequalities will be made of three parts, and the central part is compared, or is being compared by, or compared with two different polynomials. So the first example is sort of simpler, and as you can see here, you have just constant numbers. So we're going to get started with this so that we can learn the process first, and as we make more progress, we're going to learn how to complicate this a little bit more. So let's take a look at our example 5. We have to solve the double inequality, and we have to draw the answers on the number line. So the way that this is going to work is simplifying each part of the inequality. As you can see here, we have three parts of it. So we have the left, we have the center, and we have the right side of it. So the left and the right side don't need any simplifications, but the center does. And we want to write these parts in linear form, more simplified linear form. So 30 will sit where it is. And inside here we have 6x and then plus 12. So this is where they come from. And then we have negative 2x minus 2. That's then or equal to 46. Now, we have to combine like terms, so we have 6x minus 2x is 4x. 12 minus 2 is positive 10. So less than or equal to 46, greater than or equal to 30. Now, I want you to think about it, and it's something you can figure out on your own whenever you learn something new. Always think, what part of this new thing is familiar to me? So what part of the solution, so how far can I go in solving this? And as you go through this process, you will probably most likely figure out that you would be able to figure out even the step that you've never been taught or learned. And even if you don't, at least guessing about the next step will push your brain to think a little bit harder. And this is where learning begins, like true learning begins. True learning is independent thinking, believing in you knowing how to do things, believing in you or having faith in yourself that you can figure things out on your own, and that increases the persistence. So I'm going to continue here. And what we have is 4x plus 10 has to be less than or equal to 46 and greater than or equal to 30. And these conditions must be satisfied simultaneously. There are two different methods of solving from here. I'm going to explain the easy one. I want you to think, when I solve a regular inequality, what do I normally do? Well, I have to solve for the variable. My goal is to isolate the variable, and the variable is right here in the middle. So now I'm thinking, okay, so if I am here, like if my variable is right here in the middle, then that means that I first need to get rid of the constant terms. So the next step would be to remove the constant term from the middle part of the inequality. Now remember, we don't remove the constant term and take it to one side or the other, whichever side we prefer. To maintain the inequality throughout this expression, or to maintain the double inequality, whatever happens to the middle should happen to the right and to the left. Now, this is very important to remember because we're so used to thinking that, okay, so I am taking, let's say, for example, if you say x minus 2 greater than 0, I am taking negative 2 to the other side. But that's not exact definition, or that's the exact meaning of what we do in this step. We're not taking the term to the other side, we're practically adding this term to both sides. So this is how I want you to think about this step in the solution. So we are adding or subtracting the number, the undesired number, from each part of the inequality. So guess what? Now we are going to say that our inequality, that is made of 3 parts, will now have 10 removed from every single part, and that is because the middle part wants to have just x in it. So now we're going to say that the middle part is 4x, 10 minus 10 is 0. Now the right end has become 36 and the left end has become 20. So now I want you to think, so what do I do to isolate x? Because that's our ultimate goal. Well, what do you want to isolate x from? Number 4. And what's number 4 doing? I mean, what's the operation with x? Multiplication. So to eliminate something multiplying a variable, we do the opposite of it, which is, or the reverse of it, I should say, which is division. So when we divide, we'll divide all 3 parts by the same number, by number 4. And we'll be amazed now to see that x is greater than or equal to 5 and less than or equal to 9. And now think about it, isn't this a solution, a legitimate solution? Like when you look at the format of this statement here, you can see and you can tell that's the final answer. And not only that, but it is given in set notation. So even though we learn interval notation as a more practical method or way, set notation is still powerful in a way that it makes a lot of sense, not to mention that is the first way we describe sets of numbers. So we're going to graph this. So we have number 5 here and number 9. So the scale is a little bit tight in here and a little bit, because 10 should be a little bit further actually. So I'm just going to mark number 9 in here. And you see that number 9 is right here. Let's make this red so it stands out. And we have number 5 as well. And all the x values here will be between 5 and 9. So this would be the solution. And in interval notation, we're going to say that the solution will be between 5 and 9. And both numbers are included in the set, so we're going to use square brackets around it. And you're done. Now, in the next question, you have another example. I encourage you to do this on your own. I will continue to solve this in the meantime. So again, we have the same idea here. We have the middle part that is carrying the variable, and on the sides, we have just constants. So 5x plus 20 minus 4x plus 6 Now we have another plus 6 in here at the very end, and we have the left and the right sides, which are 16 and 41. So let's see what we have cooked here. So we have 5x plus 4x minus 4x, or plus negative 4x. That would be x. And 20 plus 6 is 26. And we have 16 on the left and 41 on the right. Now we have to isolate x from positive 26, which means that we'll need to subtract 26 from the middle to leave x alone. And if we do that from the middle part, then we got to do that from every other part of the inequality, of the double inequality. And look at what happens now. So obviously these two will simplify. We have x on its own. 16 minus 26 will be equal to negative 10. And 41 minus 26 will be equal to 15. So as you can see here goes our solution exactly in set notation. And what we're going to do is try to draw the solution on the number line. As you can see here, we have the numbers negative 10. We do want negative 10 to be part of our solution. We have the number 15, for which we haven't made much room. I think we were too ambitious here with these coefficients, but imagine number 15 being a little bit further here. Let me just fix it. And we're going to say that, let's suppose that this is our 15. And we're going to say that all the solutions to this inequality will be in between these numbers. That's how you would graph it. And in interval notation, we're going to say that x belongs to the interval from negative 10 to positive 15. We want both of them, and that's why we're going to give them square brackets. So for the next example, I have created a thinking and inquiry question, and for this we're gonna take a look together in a separate video. So as always, thank you for learning with me, and bye for now. See you next time.